lesson for this chapter. Okay, electromagnetic waves. I'm going to show you a picture and then we'll talk about it. Okay, so it is an oscillating electric field and a magnetic field. This is H is your magnetic field. Good observation. Uh, so if you remember to electromagnetism, fun fact number 3 was if a conductor is experiencing a changing magnetic field, then voltage is induced. Okay. If you dig a little deeper into physics, what you find out is if you have a changing magnetic field, that actually creates or induces a changing electric field. Okay. And then if you dig a little deeper, a changing electric field induces or creates a changing magnetic field. But doesn't a changing magnetic field make a changing electric field? Yep. But doesn't that make a magnetic field? Yep, sure does. And so it's self-perpetuating. And this is why electromagnetic waves can go through space and don't need a medium. They're self-perpetuating. Kind of. Okay. And so this this actually obeys the right-hand rule. It's crazy. Okay. So this is like what an electromagnetic wave looks like. So how would you describe it? This is an oscillating electric and magnetic fields that are perpendicular to each other. I needed to show you that picture so you would have some understanding of what that meant. So what? Okay. Can they travel through space? Yes. No medium required. And that is a really good thing because that's how we get sunlight and energy from the sun to Earth. Okay, it travels through space. Good with that? Okay. Okay. All right. What's the speed at which electromagnetic waves travel? Speed of light. Okay. It has its own little variable, c, lowercase c, 3 times 10 to the 8th meters a second. Okay, the speed of the wave, speed is equal to frequency times wavelength. Yes, talked about that. So specifically applied to electromagnetic waves, you get that relationship there, which you used in chemistry. Good with that? Okay. This is the electromagnetic spectrum. Okay. So here that is our relationship. So they all move at the same speed, so that's fixed. Here we see wavelengths are long here and short wavelengths here. Okay, so your wavelengths are increases as you go that way and decreases as you go this way. Are we all right with that? Therefore, your frequency does what? Over here, what does your frequency do? Increases or decreases? Or stays the same? Based off of this, this is fixed. So as this goes up, this has to go down. Okay? Good with that? Okay. In chemistry, did you guys get introduced to this one, Planck's constant? Okay. So energy is directly related to frequency. Okay. So your energy increases as you go this way, decreases as you go this way. Right with that? Okay. Now, the electromagnetic spectrum is huge. We have wavelengths that are hundreds of meters, all the way down to wavelengths that are the diameter, the width, the radius of a nuclei of an atom. 1 times 10 to the second, like, so we're in the hundreds, down to 1 times 10 to the negative 12th. That is a vast array of variety of electromagnetic waves. Okay, and we've categorized them into 7 chunks, big chunks. I mean, they're just massive. Okay, so bless you. We've got radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays.
If the wavelengths are less than an atom, how do we measure them?
Great question. I don't know. Let me think about that one. Good question.
Wait a minute. So if we use radio waves instead of microwaves,
We'll talk about that here in a little bit. All right. So, is everybody good with like the vast variety? Okay, we're going to take a tour through each of these. Okay, this is more of like, this is going to feel more sciencey than mathy. Okay, so radio waves. So obviously radio, AM, FM, TVs, satellite stuff. Those are used for radio waves, long distance, things that travel long distance. Um, those are in the radio waves. Okay, this is my growing up technology. This is okay. Um, so anything that has to go long distances, we're using radio waves too. So we're talking to satellites. These are all radio waves. Okay. Um, this is yours. Okay. Next up is microwaves. Okay. Mind you, this is a broad spectrum. Okay. One of these frequencies is microwave ovens. Okay. What you cook with, Curtis. There you go. Okay. It is okay. Cell phones use microwaves, Bluetooth, Wi-Fi, anything close are using microwaves. Okay, and we use this for communication devices. Now, some people are like, wait a minute, cell phones use microwaves? Isn't that gonna like fry our brain? Okay, so there's a specific frequency that microwave ovens use, and that frequency is the natural frequency that water, H2O, resonates at. Okay, it taps into like it hones in and like, hey, let's use it, and so it gets water molecules jiggling, and that's what warms up your food. Okay, um, that's why you put some water in whatever food you're trying to warm up for a microwave. It heats more evenly. Don't know if you've noticed that, but you should try that. You don't do a ton of water, but like put some water in there, stir it up, and it'll heat better. Okay,
What's the natural frequency of like people?
you're made of mostly water.
So if I go like in the microwave, you know, okay.
That's why people explode in the microwave.
Yeah.
That actually makes a lot of sense now.
Okay.
I'm in a class
Uh, all right. So we stay way away from that natural frequency of water for cell phones. Remember the tuning forks? How you hit one and it caused the other one to resonate, and then you change the natural frequency of one and you hit it and it didn't touch the other one. Okay, that's why. Like, this is why cell phones are safe. Okay, now if you put one to match that, yes, that would be horrible. Okay, yes, Curtis.
How come like metal in a microwave like causes any explosion?
It causes. That's a good question. That it causes current to be flowing in the metal.
Okay, but how come the sides of the microwave, like the inside of it, is metal? How come that doesn't cause?
There's not sharp edges.
So if you put like a round piece of metal, it wouldn't.
Yeah.
That's cool.
So like, what if like someone like weaponized it, have like a little gun that like shoots like microwave? Would that actually work, or is it just like?
You're talking about some Cars 2 type stuff. That's like exactly what they do.
Is it really? Yeah, I watched Cars 2.
Yeah, the radar.
But like, would that work, or does it just not like not work at all?
I think it'd do more harm than good to people shooting it because they're closer. But yeah, bullet would be more effective.
No, I guess so.
And it'd be like, oh, dude, why am I? This feels weird, and like, it's not quick. All right, so Wi-Fi, Bluetooth, all that stuff. Okay. That that's not a bad idea. Like, okay, radar also, like radar guns. Um, that's also microwaves. Good. Anything close, communication, microwave. Okay. Next up is infrared. This is the next general category. Um, so your remote controls go off of infrared. Okay. So this guy right here. Okay. Um, oh, you can see that. Okay. So can you see that light? You see this light bulb? See it blinking?
No.
Nope, because you can't see infrared.
Wait, then why do I see my TV remote blinking?
I don't know. My guess is some part of that's visible, but this is your camera can pick it up. See that? Tell me if I'm missing my. See that? Okay, that signal is shining light, and but we can't see that part of the spectrum. Good with that? Okay. So there's another part of the infrared waves that deal with heat. Okay, which we'll talk about later this year. Um, so anything that's above absolute zero emits infrared waves. Predator, this is how Predator sees. Um, so if you have a thermal imaging camera, you can do some really cool stuff with it. Like you can see where like you have a clog in your pipe, you can pump hot water down it and see where it stops. And like, oh, there's the blockage right there. Or you could like see where you're losing heat, see things out in the woods. You can do electrical problems. Pretty cool device to have. Okay, good with that. Okay.
Wait, so like, if animals see like that, can they like see me across a wall? Like if I'm like in a wall,
Yeah.
can they see me?
Yeah, but they don't.
But they don't.
He said predator.
Like the movie Predator.
Oh.
Not
I
like.
was like, I was confused for a second. So like, I don't
Sorry.
want to be like.
I'm hiding. Like, jump through the wall and eat you. Yep, that's why the movie is scary. All right, so visible light. We'll talk about this more next chapter. It will be on light. Um, but this is this color spectrum: Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. I'm more of a Crayola kind of guy, like blue, purple, like Roy G. Biv, like, but whatever. So you have long wavelengths here, low frequency, short wavelengths, high frequency for this spectrum. Okay, but notice how small of a chunk that visible light is to our electromagnetic spectrum. This is the only part that our eyes are sensitive to. Good with that? Okay. Now, um, next up is ultraviolet. This is after violet. This is ultraviolet. We don't see into this, but insects do. Okay, that's why bug zappers are that purple light. So we're seeing the part that we can see. There's a whole nother part that's shooting out that we can't see, but bugs can.
So those things really just blind them?
No, it attracts them. They like light.
Oh.
Why can we only see so few, like such little of the spectrum?
That's just how our eyes are designed. And we'll talk about like cones and rods. That's just the wavelengths that our eyes resonate or are sensitive to.
Does the color of your eyes affect how you see?
No, not that I'm aware of. Okay, so ultraviolet also has to do with like sunburns, cancer beds. Okay, um, so ultraviolet. um, so this part's good. This part's bad. This is more energetic. This is the stuff that gives you cancer, skin cancer. Okay, our ozone layer, our atmosphere, blocks most of that out. So we should probably take care of our ozone layer. Doing stuff that like deteriorates that, just not a good idea. Okay, and let me talk to you. Like, let me show you. Okay, you see this light blue squiggly stuff. Okay, this is the stuff that this stuff, this, and this gets blocked by our atmosphere. This stuff over here gives us cancer because it has more energy associated with it. This gets blocked by our atmosphere. This is what gives us cancer. This is what's blocked by our atmosphere. We should probably do things to like preserve our atmosphere. Be a good idea. Not to do things that would be detrimental to our atmosphere for the sake of our kids, grandkids, generation. Like, yeah, good luck, kids. Yes, Curtis.
Doesn't it heal itself though?
No, where is it going to heal from?
I don't know, but supposedly like
It's
in
not.
the
It's not a.
1970s there was like a huge hole in it, and now the hole's almost gone.
It's not a. It's not a. It's not a live thing.
The hole's gone. Supposedly. How the hell do you repair it? You send up a space shuttle and
I need to look into that before I would speak to that. Have you looked into that, or did you just hear somebody?
No, I don't know. It was a whole NASA thing. They did a huge a deal about how the atmosphere had a huge hole in it, and like it was like 76 or something. After they launched a couple rockets and then like now they like did a test and the hole's like essentially gone. Like it's completely, there's no hole anymore.
Okay, I'll have to look into that. All right, so here's some other cool stuff. So visible light gets through. This is what enables us, we can see the stars. If light couldn't get through, we wouldn't be able to see the stars. That's really cool. Okay. So when we're trying to find other life on other planets, we're using radio waves because radio waves get through. We can receive and give radio waves through our atmosphere, and they travel long distances. Here's that. All right. Next up are X-rays. So, uh, X-rays. The reason why X-rays work is because they have a higher frequency and a lower wavelength, and so it gets through soft tissue, but it doesn't get through dense tissue like bone. This is actually a photograph of an X-ray. So they shoot X-rays through your hand, and it gets through the skin and the muscle part, but it gets stopped by the bone. And then to look at this, what they do in photography terminology, we take the negative of this picture. This is what we do to be able to look to see if there's cracks in a bone or not. Okay. Now, getting X-rays isn't good. This is these are energetic things that could give you cancer. Okay. That's why they put that lead smock on you to protect you from those X-rays. That's why the people doing the X-rays walk out of the room, so they don't want to get exposed to that time and time and time again. Doing a couple of X-rays, it's not great, but it's like, you know, eating chocolate cake isn't great for you either. But but you don't live on chocolate cake. That's just dessert. Does that make sense? Like you just kind of deal with it. Um, so uh, I guess real quick here, I had this thought. So this in a microwave, you know how there's like this screen that looks kind of like a cheese grater? That looks like a mirror to microwaves. Some of it does get out. Like if you, so I wouldn't like, is my food done yet? I don't know. Like I wouldn't do that for a long period of time. Okay.
So we can't answer, or would your head explode?
Your head would resonate, like kind of, it wouldn't be a cancer thing. It'd be a water vibrating type thing. Okay. Okay. Next up, last is gamma rays. We associate this with nuclear radiation. The 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 reality is, in science terms, this is all radiation, the whole spectrum. Okay, but this is the stuff that gives you cancer. All like ultraviolet on is all gives you cancer, but this is the stuff for like, ugh, this is scary stuff. Yes, like if you get cancer treatments, this is gamma rays. They're shooting at you. Okay, radiation. Um, yeah, go to that. So if you could see into the electromagnetic spectrum, this would be what the sun would look like. Now they've color coded these just to make it look cooler. This is what the sun's spitting out: radio waves, microwaves, infrared. I don't know why they didn't make this yellow. I mean, it's like, whatever. Ultraviolet, X-rays, and gamma rays. X-rays, that is pretty sick. I mean, it's like, dude. Okay.
It's like it seems something infrared or X-ray would be creepy.
It would, yeah. There's lots of things that are. Okay. Give that one a shot. Everybody good with E? They're all going at the speed of light. Okay. D. Okay. A. D. Okay. Here's what you're responsible for. Knowing the 7 categories, know their order, and knowing their order in terms of energy, frequency, wavelength, how they stack up. Good with that? Um, so I feel like, yes, that's factoids, but there are some factoids that are worth knowing in life. Like you're exposed to that. I think that's fair enough to like you need to know these. Okay. All right. So an application of this. So it's a wave. It experiences Doppler effect. This is how we discovered that the universe is expanding. Okay. We looked at stars, and I've been told that you guys didn't do this in chemistry, or some of you didn't do this in chemistry, which is sad. Well, I'm gonna have to make this up to you. But like, if you looked at spectral lines, each chemical when it's burned gives off a certain color signature, and you can look at spectral lines, and it's like a chemical signature. Um, and we know what stars are made out of, and like, hey, this burns this way. And when we looked at the chemical signature, the green was like shifted over a little bit, ever so slightly. Blue, like what? Sorry, whatever these colors are, they're shifted over ever so slightly towards the red end of the spectrum, redshift. And so people are like, why is that? And they're like, well, they threw out this idea, well, maybe it's moving away from us and it's experiencing a Doppler effect where it has a lower frequency. And as they studied that and as they tested that, they're like, yeah, every experiment that we do lines up with that idea that the universe is expanding. Stars are moving away from us. Go with that. Okay. And so, so is it expanding? So as they're measuring, is it expanding at a constant rate because of momentum? Like, nope. Is it expanding? Is expansion slowing down because gravity is like, hey, come on back here? Nope. It's actually accelerating. Yep. Our expansion of the universe is accelerating. Okay. Why? We don't know. We're going to call it dark energy. Okay. Because we haven't measured, we don't know how to measure that yet. It's just kind of out there. Okay. Um, it acts like an inverse gravity, pushes things away. Okay. So how much dark energy is there? Um, so this, so in the first part of the history of the universe, this is the rate of expansion. Okay, like from the explosion. Okay, but then after here, it started to accelerate outward. Okay, we can look back into space. As we look back in space, we're looking back in time because it took. So when you see the sun, it's what the sun was 8 minutes ago. As you look at the stars, the nearest star, Alpha Centauri, that's what it looked like 2 years ago. Sorry, is it 2 years? Factoids, come on. I think it's 2 years, 2 light years away. Okay. As we look at things further and further away, we're looking at what they look like longer and longer ago. Does that make sense? So that's what that whole James Webb telescope was all about. Like, I want to look as far back as we can. Okay. Um, so turns out that of known stuff, only 30% is matter. 70% is this dark energy stuff. Of matter, 20% is the stuff that we can measure. There's 80% that's dark matter. So dark energy, dark matter, different things. Okay. Um, so we don't know much. Okay. So dark matter is the stuff. So if you look at different things, we would expect this to go faster than this out here, just like Mercury goes faster than like Neptune. But it turns out everybody moves at the same speed around Milky Way galaxy. Why? Oh, dark matter is the reason. We don't know. Okay. So dark energy is like the anti-gravity. Okay, so there's this fine line, this balancing between gravity and dark energy. Because if it expands too much, like things don't form, and if it expands too less, then like things don't form. And this is a very brush over thing. Okay, um, that ratio of dark energy to gravity has to be just so. It's like 1 to the 10 to the 120th chances that our universe exists. What does that mean? Just to like throw this to like mind boggle your eyes. Okay, in a sandbox, there is 100 billion grains of sand, just sandbox. I want you to pick one of those out, one grain of sand out of all of those. That's 1 times 10 to the 11th chance that you pick the right grain of sand. Okay. Okay, so all the grains of sand on all the world's beaches and deserts, 1 times 10 to the 19th. Notice we just went from a sandbox to all the like all the sand on beaches and deserts, all that stuff. We just went from that to that. Oh, so cool. Okay, so like that, so small of a chance. Okay, so there's approximately 1 times 10 to the 24th atoms. Did I do this?
Yeah, you've done this already. Like a couple. You did this like a few weeks.
At the beginning of the semester? Okay, some classes I didn't get to.
So sorry, like there's like the one in like
Yes.
the 90 chance of like our universe.
And here we are.
Seems
Are
like
we gonna
a
have to
little
know
bit
that
too
for
big
the
of a
test?
chance.
Do what?
Are we gonna have to know it's
No.
going to the 10 or?
No, no, no. No.
Finally, it seems like too big of a chance.
It's crazy. Yeah.
Your video from yesterday was private. I couldn't watch the notes.